In 2024, a bridge opened in China that contains almost no steel at all. Not a reduced amount, not a clever redesign that uses less. Almost none. And it is carrying traffic right now, every single day, in a country that produces more steel than the rest of the planet combined. That sentence alone is enough to make a lot of engineers uncomfortable. Because for the last 150 years, steel has not been one option among many. Steel has been the answer. Every skyscraper, every bridge, every tunnel lining, every power plant, every port crane, every railway line on Earth is built around the assumption that steel is the strongest, cheapest, most reliable thing humans know how to make. And now, China is quietly building things that ignore that assumption entirely. When German engineering journals first started publishing the test data coming out of Chinese laboratories, the reaction was not excitement, it was disbelief. Some of the numbers being reported were 4, 5, even 8 times higher than what conventional materials could achieve. Several European researchers openly suggested the results had to be measurement errors or lab conditions that would never survive the real world, or simply exaggeration. Then the bridges opened. Then the tunnels went into service. Then the offshore platforms started taking waves in the South China Sea. And the conversation changed from, "This cannot be real," to "How did we not see this coming?" If you are enjoying videos like this one, hit the like button, because these take an enormous amount of research to put together, and subscribe so you do not miss the next one. What follows is the story of how a material almost nobody outside of a laboratory had heard of 20 years ago is now quietly replacing the backbone of modern construction. But to understand why China went looking for an alternative to steel in the first place, you have to understand the problem that steel has never been able to solve. Steel is extraordinary. Nobody serious disputes that. It is strong in tension, meaning you can pull on it hard and it will not snap. It bends before it breaks, which gives you warning before a collapse. It is weldable, recyclable, predictable, and after a century and a half of refinement, engineers understand its behavior better than almost any other material on Earth. But steel has one fatal flaw, and every engineer on the planet has known about it since day one. Steel rusts. That sounds almost too simple to be a real problem. Rust is what happens to a bike left out in the rain. But when you scale that up to national infrastructure, rust stops being an annoyance and becomes an economic disaster measured in the hundreds of billions of dollars every single year. Here is what actually happens inside a modern bridge. Concrete on its own is strong when you push on it, but weak when you pull on it. So engineers embed steel bars, called rebar, inside the concrete. The concrete handles the pushing, the steel handles the pulling, and together they make a material far better than either one alone. This combination, reinforced concrete, is arguably the single most important building material of the 20th century. Nearly every large structure you have ever walked into contains it. But concrete is not waterproof. It is porous. Over years and decades, water seeps in. It carries oxygen with it. It carries road salt from winter de-icing. It carries chloride from ocean spray. And when that mixture reaches the steel bars buried inside, the steel begins to corrode. Now, here is the part that turns a small chemical reaction into a structural catastrophe. When steel rusts, it expands. Iron oxide takes up significantly more volume than the original metal did. So a steel bar buried inside solid concrete starts swelling from within, pushing outward with enormous pressure against the concrete that surrounds it. The concrete cracks. The cracks let in more water. More water means faster corrosion. Faster corrosion means more expansion, which means bigger cracks. It is a feedback loop that accelerates itself, and once it starts, it does not stop. Engineers call it concrete cancer, and the name is accurate. The structure begins destroying itself from the inside out, invisibly, for years before anyone on the surface notices a single stain. By the time you can see rust bleeding through the underside of a bridge deck, the damage inside has usually been advancing for a decade. This is not a hypothetical concern. In the United States, Tens of thousands of bridges are rated as structurally deficient, and corrosion is the dominant cause. Germany, a country genuinely obsessed with engineering quality, has been fighting a long and expensive battle to keep its Autobahn bridges standing, many of which were built in the post-war boom and are now aging badly. The costs of inspection, patching, sealing, and eventual replacement are staggering, and they never end. You do not fix corrosion, you delay it. And China, building faster and at greater scale than any country in human history, was about to run headfirst into this problem at a magnitude nobody had ever experienced. Think about what China built between roughly 1995 and 2020. Tens of thousands of kilometers of high-speed rail, bridges across every major river, entire new cities, ports along a coastline thousands of kilometers long, tunnels through mountains, sea crossings that stretch beyond the horizon. Every single one of those structures came with an invisible bill attached, payable decades later in maintenance, and a very large share of it was built in the worst possible environment for steel. Coastal China is hot, humid, and salty. Salt air is one of the most aggressive corrosion accelerators that exists. A bridge in a dry inland climate might last 80 years before serious corrosion issues appear. The same bridge in a marine environment might show significant deterioration in 20. Chinese engineers ran the numbers and found something genuinely alarming. If the country continued building the way it had been, the maintenance burden alone, just keeping existing infrastructure from falling apart, would eventually consume a meaningful percentage of national construction capacity. They would spend a generation just repairing what the previous generation built, with nothing left over to build anything new. That is the trap, and it is a trap that Europe and North America are already deep inside. Enormous portions of Western infrastructure budgets go to maintaining structures built 50 and 60 years ago, not to building anything new. So around the early 2000s, a question started being asked seriously in Chinese research institutes. Not, how do we protect steel better, but something far more radical. What if we stopped using steel? Now that idea was not new. Materials that could theoretically replace steel reinforcement had existed in laboratories since the 1960s. Fiber-reinforced polymers, carbon fiber composites, basalt fiber, aramid, they were known, they were understood. They were also, at the time, wildly, laughably expensive. Carbon fiber was aerospace material. It went into fighter jets and satellites and Formula One cars. The idea of burying it inside a highway bridge was economically absurd, like paving a road with titanium. Western engineers had done the studies, confirmed the material worked beautifully, noted the cost, and filed it away as an interesting curiosity for special applications only. That was the correct decision. In 1995, but China looked at the same problem from a completely different angle. Instead of asking whether the material was affordable today, they asked what would happen if someone decided to manufacture it at the same scale they manufactured everything else. And that changed everything. Here is the thing about advanced materials that almost nobody outside of manufacturing truly appreciates. The price of a material is not fixed by physics. It is fixed by production volume. Aluminum was once more precious than gold. It did not become cheap because someone discovered new deposits. It became cheap because someone figured out how to make it at industrial scale. The same thing happened to solar panels. The same thing happened to lithium batteries. And China has demonstrated, over and over, that it is extraordinarily good at taking an expensive laboratory material and dragging its price down through sheer manufacturing scale until the economics flip completely. So they started building carbon fiber production capacity, quietly, steadily, for years. Before we go further, let us actually talk about what these materials are, because the physics behind them is genuinely remarkable, and it explains why the German reaction was disbelief rather than dismissal. Take a carbon fiber reinforcing bar. Visually, it looks a bit like a black plastic rod, sometimes with a ribbed or sanded surface, so it grips the concrete properly. It is not one solid piece. It is made from thousands upon thousands of individual carbon filaments, each one thinner than a human hair, all aligned in the same direction and locked together in a resin matrix. That alignment is the entire secret. In steel, the atoms are arranged in a crystal structure that is roughly the same in every direction, which means steel is equally strong no matter which way you pull it. That is convenient, but it also means you are carrying material you do not need. In a carbon fiber bar, essentially all of the strength is pointed in one direction, the direction the load actually travels. Nothing is wasted. The result is a material with a tensile strength that can exceed conventional reinforcing steel by a factor of 2 to 4, at roughly 1/4 of the weight. One worker can carry a bundle of it that would require a crane and a crew if it were steel. And then there is the part that actually motivated the whole project. Carbon fiber does not rust, it cannot. Corrosion is an electrochemical reaction specific to metals. Carbon fiber composite is not a metal. Salt water does nothing to it. Road salt does nothing to it. Ocean spray does nothing to it. You can immerse it in seawater for decades and it simply does not care. Basalt fiber is the same story from a different direction. Basalt is volcanic rock, one of the most common rock types on the surface of the planet. You melt it at around 1500 degrees Celsius and extrude it through fine nozzles, and it comes out as continuous fiber. No complex chemistry, no rare inputs, no exotic supply chain, just melted rock, spun into thread, and it is chemically inert, fireproof to extreme temperatures, and immune to the corrosion that eats steel alive. There is also a third piece to this puzzle, and it might be the most important one: ultra-high-performance concrete. Ordinary concrete is essentially a rock glued together with cement paste. It has voids. It has microscopic gaps. Those gaps are the highways that water and chloride travel along to reach the steel inside. Ultra-high-performance concrete attacks that problem directly by packing the particle sizes so tightly, using extremely fine powders alongside normal aggregate, that there is almost nowhere left for water to go. The compressive strength jumps enormously, sometimes 5 to 8 times that of ordinary structural concrete. But the real prize is permeability. This material is so dense that water essentially cannot penetrate it. Chloride cannot migrate through it. Combine that with reinforcement that cannot rust anyway, and you have removed the corrosion failure mode from the equation entirely. Not reduced it, removed it. That is the claim that made European researchers push back so hard, because the entire design philosophy of Western infrastructure is built around managing deterioration. You assume the structure degrades, you build in safety margins, inspection schedules, maintenance cycles, and a projected service life. Telling a room full of experienced structural engineers that you have a system with no meaningful corrosion mechanism sounds less like an advance and more like a sales pitch. And to be fair to the skeptics, they had real technical objections, and some of them still stand. The biggest one is ductility. Steel is beautifully forgiving. Load it beyond its design limit and it stretches, it sags, it groans. It gives you visible, unmistakable warning that something is wrong before it lets go. That property has saved an incalculable number of lives because it turns sudden collapses into slow failures that people can escape from. Carbon fiber does not do that. It is elastic right up until it is not. It holds its shape and then fails suddenly and completely. Engineers call it brittle failure, and in structural design, it is close to a dirty word. That is a legitimate concern, and Chinese engineers do not pretend otherwise. The answer they developed is layered. First, hybrid designs, where carbon fiber handles the primary tension load but steel or ductile fibers remain in specific zones to provide warning behavior. Second, embedded sensor networks. If the material will not warn you by sagging, you instrument it so it warns you with data. Fiber optic strain sensors are cast directly into these structures during construction, monitoring strain continuously, feeding readings to control centers in real time. It is a genuinely different philosophy. Western practice says the structure should warn you physically. Chinese practice on these projects says the structure should warn you digitally, and it should warn you years earlier than sagging ever would. The second objection was cost. And this is where the story gets interesting, because the skeptics were absolutely right for about 15 years and then abruptly stopped being right. In the early 2000s, carbon fiber reinforcement cost something like 10 to 20 times what equivalent steel cost. No public infrastructure agency on Earth could justify that. It did not matter how good the material was. But China did not treat that as a permanent condition. It treated it as an engineering problem. Enormous production facilities were built, domestic precursor chemical supply chains were developed so the raw inputs did not have to be imported. The energy-intensive carbonization furnaces, which are the most expensive part of the process, were redesigned for continuous high-volume operation instead of small batch runs. Automated weaving and pultrusion lines replaced manual layup. Every single step got optimized for scale rather than for the small precision runs that aerospace demanded. And the price fell. Not gradually, it collapsed. Meanwhile, something was happening on the other side of the equation that almost nobody factored in. Steel was getting more expensive to use, not in raw price, but in total lifetime cost. Environmental regulations tightened on steelmaking. Carbon pricing began appearing in more markets. Labor costs for the constant inspection and maintenance that steel structures require kept climbing everywhere in the world. At some point in the late 2010s, in specific applications, the two curves crossed. And the moment they crossed, everything changed. Because when you compare these materials over the full lifetime of a structure rather than just on day one, the comparison is not close. Consider a coastal bridge. Conventional design, steel reinforced concrete. Initial construction is cheaper. Then you begin the endless cycle. Inspections every few years. Protective coating reapplication. Cathodic protection systems that require power and monitoring. Crack sealing. Eventually partial deck replacement, then major rehabilitation, somewhere around year 30 or 40, and at some point, complete replacement, along with all the traffic disruption and economic cost that comes with closing a major crossing. Now the composite version. Higher initial cost, though far less than it used to be. Then, over decades, dramatically reduced maintenance, reduced inspection requirements, no corrosion-driven deterioration. Projected service life not of 50 years, but of 100 or more. Run that over a century, and the composite structure is not slightly cheaper, it is cheaper by a wide margin. The problem is that almost no procurement system in the world is designed to think that way. Government budgets are annual, political terms are short. A minister who spends 30% more today to save 80% over the next 100 years has made a brilliant decision that will be credited to someone not yet born. Every incentive pushes toward the cheaper option today. China's planning structure, whatever else you want to say about it, is unusually willing to accept a higher upfront cost for a payoff measured in decades. That is not a technological advantage. It is an institutional one, and it may matter more than any of the chemistry. So where is this actually being used? Because a laboratory result is one thing, and a load-bearing structure carrying traffic is something else entirely. Start with marine infrastructure, because that is where the case is overwhelming. Port facilities, seawalls, offshore platform foundations, bridge piers standing in salt water. These are the structures that die fastest. A conventional concrete pier in a tidal zone, where it is alternately soaked and exposed to air, faces the most aggressive corrosion environment that exists in civil engineering. Chinese ports have been installing composite reinforced elements in these zones for years now, and the inspection data coming back shows essentially no deterioration, where conventional structures of similar age would already be showing distress. Then, bridge decks. The deck is the part that suffers most, because it takes direct traffic loading, direct water exposure, and in northern regions, direct application of de-icing salt. Replacing deck reinforcement with composite bars removes the primary failure mechanism entirely. Tunnel linings are another major application, and there is a clever secondary benefit here that took people by surprise. Steel reinforcement interferes with electromagnetic signals. In tunnels carrying modern rail systems with sophisticated signaling and communication equipment, a non-conductive reinforcement is not just about durability, it genuinely improves signal performance. And then there is repair and retrofit, which might be the single largest market of all globally. You do not have to build a new structure to use these materials. Carbon fiber sheets and strips can be bonded directly to the surface of an existing aging concrete structure, adding tensile capacity where corrosion has stolen it. It is a fraction of the cost of replacement, and it can be done in days rather than years. China has retrofitted an enormous number of older bridges and buildings this way, buying decades of additional service life from structures that would otherwise have been demolished. That last application is the one Western countries have actually adopted most eagerly, because it fits neatly into existing budgets and does not require rewriting design codes. And design codes, it turns out, are the real battlefield. Here is something people outside the industry rarely appreciate. Engineers do not simply choose materials based on performance. They are legally and professionally bound to design according to established codes and standards, documents built over decades, backed by enormous bodies of test data and, frankly, by accumulated experience of past failures. Those codes exist because people died when structures were designed without them. For steel-reinforced concrete, those codes are mature, exhaustive, and trusted absolutely. For composite reinforcement, they are newer, thinner, and in many jurisdictions still incomplete. So, when a German engineer looks at Chinese composite structures and says, "I would not sign off on that," it is usually not stubbornness or nationalism. It is that the code framework they are legally obligated to work within does not fully cover it yet, and personal liability for a structural failure is career-ending and potentially criminal. No individual engineer is going to gamble on being the first. That creates a slow, cautious, entirely rational process in Europe and North America. Small pilot projects, long monitoring periods, committee reviews, gradual code development. It is genuinely good practice and it prevents disasters. It is also extremely slow. China took a different path. Build at scale, monitor intensively with sensors, gather field performance data from thousands of real structures rather than dozens of laboratory specimens, and let the data drive the standards rather than waiting for the standards to permit the data. There is a real risk in that approach, and it would be dishonest to pretend otherwise. If a systematic flaw exists in these materials that only appears after 40 or 60 years, something like long-term resin degradation under sustained load or unexpected behavior in extreme heat, China will have built an enormous amount of infrastructure containing that flaw before anyone knows. The oldest composite reinforced structures anywhere are only a few decades old. Nobody has 100-year data because 100 years have not passed. The skeptics are right about that. It is the strongest argument they have. Time is the one test you cannot accelerate in a laboratory, and no amount of manufacturing scale fixes it. But there is a counter-argument, and it is not weak. The failure mechanisms of steel-reinforced concrete are known with absolute certainty. There is no uncertainty at all about whether steel and coastal concrete will corrode. It will. The only question is how fast and how much it costs to delay it. So the choice is not between a proven safe option and an unproven risky one. It is between a known and expensive certainty and an unknown that has performed extremely well so far. There is also a strategic dimension here that has nothing to do with concrete at all. Carbon fiber is not just a construction material, it is a defense material. It goes into aircraft structures, missile casings, submarine components, drone airframes, satellite structures, and pressure vessels. For decades, the highest performance grades were controlled by a small number of Japanese and American producers, and export restrictions were real and enforced. By building enormous domestic carbon fiber capacity, primarily justified by civilian construction demand, China solved that dependency as a side effect. The construction market provided the volume that made the factories economically viable. The factories provide capability that extends well beyond construction. Whether that was the plan from the beginning or a fortunate consequence is genuinely unclear from the outside. But the outcome is the same either way, and it is not lost on defense analysts in Washington and Berlin. There is an environmental dimension too, and it cuts in more than one direction. Steel production is one of the largest single industrial sources of carbon dioxide on Earth, responsible for something in the range of 7 to 9% of global emissions. Cement is another few percent. Between them, the materials that build the modern world account for a startling share of the total. Composite materials are not automatically clean. Carbon fiber production is extremely energy-intensive, and the precursor chemicals are petroleum-derived. If you build a composite structure, and it lasts the same length of time as a steel one, you may not have gained anything environmentally at all. But the calculation changes completely when the service life doubles or triples. Building one bridge that lasts 120 years instead of 3 bridges that each last 40 is a genuine reduction. It also eliminates the emissions from the constant maintenance activity. The trucks, the equipment, the material, the traffic delays. Across all those decades, the reason this story matters is not really about China versus Germany or East versus West. It is about a specific pattern that keeps repeating, and about who notices it in time. The pattern goes like this. A superior technology exists. Everyone in the field knows it exists. It has been studied, documented, published in journals that anyone can read. But it is too expensive, so it stays in the laboratory. Most institutions look at the price and conclude the technology is not ready. One institution looks at the price and concludes the manufacturing is not ready, which is a completely different problem with a completely different solution. Solar panels followed that path. Lithium batteries followed that path. Electric vehicle drivetrains followed that path. In every case, the technology was not invented in the place that ended up dominating it. What was invented was the ability to make it cheaply, in volume, reliably, over and over. Structural composites appear to be following the same path right now, and the difference this time is that the stakes are the physical skeleton of the built environment. If these materials become the default for major infrastructure over the next 30 years, then whoever controls the production capacity controls something more fundamental than any individual product. They control the ability to build. There is another version of the future where a bridge built today in a Chinese coastal province is still standing, uninspected and unbothered, in the 22nd century, while the bridge built the same year somewhere else has already been demolished and rebuilt twice. We will not know which version is true for a very long time. That is the frustrating thing about infrastructure. The experiment takes a lifetime to run, and you cannot stop it halfway through. What we do know is that the disbelief phase is over. The question in European and American engineering circles is no longer whether these materials work. That argument ended when the field data started coming in. The question now is how quickly the codes can be updated, whether domestic production capacity can be built, and whether procurement systems designed around annual budgets can be reformed to think in centuries. Those are not technical problems, they are institutional ones, and institutional problems are usually much harder to solve than material science. Steel is not obsolete. It will not be obsolete in our lifetimes. It remains the best material available for an enormous range of applications, and the global steel industry is not going anywhere. Anyone claiming otherwise is exaggerating for attention. But steel's monopoly is over. For 150 years, there was no serious alternative for structural reinforcement. Now there is. And in the specific environments where steel has always struggled most, the salt, the water, the heat, the places where corrosion has quietly consumed trillions of dollars of human effort, the alternative appears to be winning. That is not a small thing. That is a foundational shift in how the physical world gets built, happening right now, mostly out of public view, in ports and tunnels and bridge decks that nobody photographs and nobody writes headlines about. The most important engineering revolutions are almost never the loud ones. They are the ones buried inside the concrete, where nobody can see them, quietly refusing to rust. If you found this interesting, leave a like and subscribe. Every week we break down the technologies, industries, and engineering decisions that are reshaping the world while almost nobody is paying attention. Turn on notifications so you do not miss the next one, and there are related videos on screen right now if you want to keep going. So here is a question for you. If you were responsible for a country's infrastructure budget, would you pay 30% more today for something that might last 3 times longer, knowing you will never be around to find out if it worked? Let me know what you would do in the comments.